Welcome back. So today we're going to keep talking about GPUs, and we're going to look at a class of operations on GPUs called intrinsic operations. And we're mostly going to focus how we can use intrinsics to solve different types of synchronization problems. So in terms of synchronization, remember that we talked about the race condition problem in the context of distributed memory and shared memory programming. So basically, whenever you have multiple threads, then the threads each execute a sequence of operations, but when you run the multiple threads together, these operations get interleaved in some way, right? And different interleavings can perhaps cause incorrect behavior of the program. And so this can happen in GPUs just as well as it can happen in distributed memory or shared memory settings. And so, for example, if we look at the program on the right, then what's happening here is that, so this is a GPU kernel, and we have this shared variable called DA. So this is a global, so it's a global memory variable, so all the threads in the GPU can access this variable. And what we're doing is we're starting 1,000,000 threads in the GPU kernel, right? So we're starting 1,000 thread blocks with 1,000 threads each. And what the threads are supposed to do is that, so each thread just takes the shared variable and increments it by 1. And so our goal is that in the end, the shared variable has the value 1,000,000, right? Because we started 1,000,000 threads and they each increment this value by 1. Okay. But what can happen if you run this in practice is that you can get a very different value. So for example, you might end up with a value 88. Okay, and the reason you could end up with 88 is because, so here, this increment operation, right? Even though it looks like all you're doing is you're just taking a value and adding 1 to it, right? When you actually execute this instruction, it consists of multiple smaller instructions. And these smaller instructions can be interleaved in some strange way. And different interleavings can basically cause the value of DA to be overwritten instead of incremented. And so, and so when you run this, you could overwrite this value many, many times and only increment it 88 times. And so that's why you get this incorrect answer at the end. Okay, and to deal with this on the GPU, we can use certain operations called intrinsics. Okay, so these are atomic intrinsic operations. So there are other types of intrinsic operations on the GPU, for example, for doing different math functions like square root or exponential or something. So those we're not going to focus so much on those. We're only going to be looking at the atomic intrinsic operations. So these atomic intrinsic operations, they basically work like little critical sections. Okay, so they can allow you to take a piece of code and then sort of put that into a critical section so that when you execute this concurrently with many other GPU threads, you get the right answer. However, there's a limit on the nature of these critical sections, which is that if you use these intrinsics, the critical sections are only for very sort of small pieces of code. In fact, they only apply to a single operation, as we'll see. Okay, so then what about critical sections for larger pieces of code, right? How do you use those on GPUs? Well, first of all, it's quite difficult to implement a general mutual exclusion algorithm on GPUs. And then also, even if you could implement such an algorithm, when you use a GPU, you want to have many, many threads, right? And if there's a block of code that's in a critical section, then when you run those threads, the threads would have to go sequentially through that block of code. And so you would get very bad performance in that case. Okay, so even if you could implement a critical section in CUDA, you wouldn't want to because of the poor performance. Okay, so let's look at these atomic intrinsic operations. Okay, so these operations are only going to apply on variables, And the variables can be stored in global memory or shared memory. So the first operation is called atomic increment. And here you give the operation an address. Okay, so so the variable is going to be stored at this address. And this atomic inc, it's going to read the current value at this address. Okay, and it's going to return this value to you. Furthermore, it's going to increment the value, okay, by 1. And all these operations are going to happen atomically. Okay, so you both get back the old value, and then the value goes up by 1. And this happens atomically. So next we have atomic add. So this is similar to atomic increment, except for atomic increment, the value only goes up by 1. And for atomic add, you can choose how much you want to change this value by. Okay, so you can have another parameter here, val, right? And so when you do this atomic add, you're going to get back the current value at this address, right? And then you're going to add val to it, right? Val can be positive or negative, right? And also you get back the you get back the current value at address, and then you also add val to it atomically. Okay, you also have atomic max. So here again, you have an address and a value, and this atomic max is going to read the current value at address, right? And then it's going to set this value to the maximum of the current value and val. Okay, and so for example, if the current value is 3 and val is 5, right? Then you're going to get back the value 3, the current value, and then the value becomes 5. Okay, but if the current value is 3 and then your val is 2, right? Then you just get back the current value 3, and then the value doesn't change because 2 is less than 3. Okay, you have this atomic exchange operation, which is going to return the current value at this address, and then also just set it to this new value, val. And then you have this operation called atomic compare and swap. Okay, so this has 3 arguments. So it's got an address, and it's got 2 values, an old value and a new value. So sorry, these should both be ints over here. Okay, so so this is a conditional operation. And so we actually saw this earlier when we talked about how to implement mutual exclusion algorithms a few lectures ago. So what it does is that it's going to read the current value at address, okay, and it's going to give you back that value. Furthermore, it's going to take that value and compare it to old, okay, to the second argument over here. And if the current value equals old, right, then it's going to set the value to be the new value. Okay, but if the current value is not equal to old, then it won't do anything. It won't change the current value. Okay, so you get back the current value, and then you compare it to old, and if it's equal, you change it to new, and if it's not equal, you don't change it. And so so this is actually a very useful operation. In fact, it's a so-called universal operation because you can use this in different ways, and this can allow you to implement basically any synchronization operation. And the reason it's so useful is basically this atomic compare and swap lets you tell if some other thread has changed the current state. Okay, so if it's changed the current state, then you're going to do one thing to make sure that nothing. You're going to do something to make sure nothing goes wrong, right? But if there is no other thread that has changed the current state, then you're going to do something else. So you just need a way to differentiate whether there is another concurrent thread that has changed the current state. And the way this compare and swap lets you do that is that, so let's say the current state is just a number, right? So if it's a number, and if I know what the current state is supposed to be, then I know that. So suppose I know that the current state is supposed to be old. Okay, assuming there are no other threads around, then the current state should be old. So then I'll do this atomic compare and swap, and I'll do and if the current state is still equal to old, then I'll change it to this new value. Okay, But if there's some other concurrent thread, right, that has modified the value of this value, right, then the value would no longer be equal to old. And in that case, when I do the cast, right, nothing will happen to the state, right? Because if the value is not equal to old, then I will not change it to new. Okay, so yeah, so we have these atomic operations and a few other ones in CUDA. Okay, so now let's see how we can use this to solve different problems. Okay, so the first problem that we'll try to solve is that we're given an array of numbers, and we just want to compute the maximum value in this array in parallel. Okay, so so the first thing that we can try is, well, we have this operation atomic max that sort of it seems like it can help us find the maximum value. Okay, so the way we're going to write this code is that we have a bunch of threads, right? So we have an array and a bunch of threads. Each thread is responsible for one item in the array. Okay, and we're gonna so it's going to be responsible for this item. So we've seen this calculation before. So this is going to allocate exactly one thread per item in the array. Okay, and then so that thread is going to read the array value, right? And it's going to store it in its register called val. And then it's going to take the value that it read and try to do an atomic max with the global maximum value right now. So the global maximum value is a shared value, right? So let's say that it's stored in the global memory. And so the threads are just trying to take the current value that they read from the array and see if it's larger than this globally maximum value right now, right? And if it is, then the atomic max operation is going to change global max to our current val, and otherwise nothing happens. Okay, so if you run this code, yeah, so this is going to work correctly, and in fact, so it doesn't depend on the interleaving at all. So for example, if you have two threads, okay, so if the first thread read a value of 4, right, and another thread read a value of 5, then then whichever order the threads execute in, right, global max is going to end up at 5. Assuming that global max is less than 5 right now. Okay, now but the problem with this code is that it's going to work very slow. Okay, and the reason it works very slow is because all of the threads are sharing this one global memory variable, right? And they're all doing atomic operations on the single variable. Okay, and what happens is if you have multiple threads doing atomic operations on the same variable, then all these threads are going to get serialized. Okay, so if you so they're going to perform the operation one by one on this variable instead of in parallel. Okay, and you know, if we have a big array, then we're going to have lots of threads, and so potentially many threads are going to be calling this atomic max operation. Okay, so so now let's see how we can improve the performance of this. Okay, so the basic idea is that the problem with the previous code is that all of the threads contended at the single global memory address. Right? So instead, we're going to try to split the threads up so that they don't have such high contention. Okay, so now in this new piece of code, instead of having one global max, we're going to have basically multiple copies of this global max. Okay. So in fact, we're going to have an array over here called local max. Okay, so local max, yeah. So you know, if we so we're going to try to split global max into multiple copies. So let's say if we split this into 100 copies, then local max would be an array of size 100. Okay, and now instead of all the threads trying to update global max, each of the thread is going to focus on sort of one location in the local max array, and it's going to do all its updates at that location. Okay, so yeah, so to give an example of this, so suppose we make local max an array of 4 values. Okay, so so let's say something like this, right? then we're going to have one set of threads which are going to be accessing this part of local max, okay? And another set is going to access different parts of local max. And the way each thread figures out which index of local max it's going to update is it's just going to take its thread ID I here and then do it modulo the number of locations or the size of local max. Okay, so here the size is going to be 4. Okay, and so they're going to do the atomic max not onto this single shared global max, but rather they're going to do it on the local max. Okay, and when they do this atomic max, they're going to get back the current value at this index, right? And they're going to compare this current value with this value val. Okay, now if the current value is less than val, okay, then that indicates that val is then that means that val can potentially be larger than global max. Okay, or let's say this another way. Let's say that old max is currently larger than val, okay, or larger than or equal to val. If old max is larger than or equal to val, then there's no way for val to be larger than global max. And if val is not larger than global max, then we don't need to do atomic max between val and global max. Okay, so the only time that we need to do an atomic max between val and global max is if the current maximum value at this array location, right? If the current value is less than val, then potentially our val is larger than global max. And in that case, we're going to do this atomic max between val and global max. Okay, so then the effect of doing this is that, well, first of all, the first atomic max, right? Now we split the atomic max between many different memory locations instead of all focusing on one single location. Okay, so the first atomic max is going to be much faster. And also, the second atomic max, well, this is still all being focused at a single location, global max, right? However, the second atomic max doesn't happen very frequently because it only happens when old max is less than val. Okay, so and if you go through this matrix, right? So if the values, sorry, not matrix, but array. So if the values in this array are basically kind of like random, right? Then it's unlikely for old val to be less than val. And so so in that case, we're not going to execute this global max too much. Okay. Now, if you execute this, it still might not perform very well because because you could still end up doing a large number of atomic maxes onto the global max. Okay, so there actually is a better method using something called reduction. However, the point of this example is to show that whenever you have these synchronization bottlenecks that happen because you're focusing too much on a single variable, the one thing you can do is to split up that variable. Okay, so yeah, so let's see another example of this methodology where you can sort of split up a variable and then improve your synchronization speed. Okay, so here we're going to try to compute a histogram. So so here we're given so the input is going to be an array of values, and we assume that there's some upper bound on these values. Okay, so first of all, we assume that let's say they're all integers, and the range is going to be from 0 to k. Right. So then now we want to count the number of occurrences of each value. So we want to know how many zeros there are, or how many how many k's there are. Okay, so for example, suppose the array is this thing over here. Okay, so now k here is 1, right? So all the values are between 0 to 1, and then what we want to output is just how many zeros there are, right? So there are 3 zeros, and there are also 2 1s. Okay, so 3, 2 is our output. Okay, so the way that you can implement this, or one way you can implement this, is using this function over here. So yeah, so here each thread begins by computing an index I over here, right? And also, so in this example, we're not going to assume that you start the same number of threads as the size of your array. Okay, so if you have an array of, let's say, 1,000 elements, maybe you only start 100 threads. So in that case, each thread will need to process 10 elements, right? So therefore, what we're going to do is we have this parameter or this value stride over here. Okay, so then basically each thread is going to start at some index, and then it's going to process that index, and then process that index plus stride. And then it's also going to process that index plus 2 times stride, and so on. Okay. So as an example of this, right. So suppose you have 100 threads, right? So suppose you number of threads is equal to 100, right? And then suppose your so let me do this in a different way. So suppose you have so block dimension is how many threads there are per block. Okay, so let's say that there are 100 threads per block. Okay, and let's say that you started 10 blocks of threads. Okay, so therefore you have 1,000 threads in total. Okay, but suppose you have 1,000,000 elements. Okay, so you have an array of size, let's say n, and here n is equal to 1,000,000. Okay, so then what you need, since you have 1,000 threads, is you need each thread to process 1,000 elements. Okay, so therefore we're going to start our threads. So the threads are going to have so they're going to compute this value I over here. So the I is going to be between 0 to 999. Okay, right, and then whatever your I is, you're going to be processing all the threads. You're going to be processing I, and then also I plus 1,000. Okay, 1,000 being equal to 100 times 10. Okay, and you're also going to process I plus 2,000, right, and so on. Okay, so so then in this loop here, what we're going to do is we're going to read a current index in the array, and then whatever value that is, right, we're going to increment that value in the histogram, okay, by 1. So we're going to do this atomic add on this location of the histogram, and then the location that we look at is equal to the current value that we look at that we're looking at. Oops. All right. So as an example of this, right? So you know, if we go through this array, then the first thread is going to see that val of 0 is equal to 0, right? So it's going to modify the histogram at 1, and it's going to set this to 1. Okay. The next thread is going to see that vals of 1 is equal to 3. So it's going to change the location. So it's going to increment the value at histogram of 3 to be 1. Right? And then you have these two next threads. So they're both going to see a value of 1. So they're both going to go to location 1 in the histogram, and they'll do 2 atomic adds at that location. So this thing will become a 2 over here. Okay, and then if you had another thread over here, right, it would go to address 0. It would go over here, and it would set this to a 2. Okay, and again, after you process your index I over here, you're also going to process I plus stride, and you keep doing this until you've processed the entire array, until I is larger than or equal to size. Okay, so yeah, so this algorithm is going to work correctly because the only contention that you can have is when you try to update these values in the histogram. Okay, but nothing bad's going to happen because we always use these atomic adds over here. Right? You could also use atomic increment. That would also be fine. However, problem again is that this is going to be slow. Okay. So one reason it's going to be slow is that maybe so currently we're storing the histogram in global memory. Okay, so accessing this histogram is going to be slow. And also, since all the threads are writing to the same histogram array, right? Then there's going to be could potentially be a lot of contention, and that can also make things slow. So therefore, what we're going to do is instead of all the threads contending on the single histogram, we're going to make multiple local histograms. Okay, so that is going to reduce the contention. And also, we're going to store these histograms in shared memory instead of global memory. Okay, so that will also improve the access speed. And then, but at the end of this computation, we need to combine all of these local histograms into one big histogram. Okay, so that final histogram is still going to be in the global memory. So we have to have this final step, which combines a bunch of shared memory local histograms into a single global memory histogram. Okay, so the code we have for doing this is like this. So here we're going to assume that there are only 256 different values in the array. Okay, so for example, the values go from 0 to 255. And in that case, we're going to make a local histogram, and the size is just going to be the number of different values there are, so 256. Okay, and we want to initialize this local histogram to all zeros. So therefore, we're just going to take the first 256 threads in our thread block, and then initialize this to initialize the values of the local histogram. Okay, so now because we're storing this local histogram in shared memory, right? Then each block of threads is going to have their own local histogram. And we want to make sure that this histogram is completely initialized before we do anything else. Okay, so we're going to put the sync threads over here to make sure that this entire histogram has been initialized to 0 before we put anything into it. Okay, so next we're going to compute a starting index for each thread, right? And we're going to compute a stride for the thread, just like before. Because again, we're going to assume that we have potentially more items in the array than we have threads. Okay, so each thread needs to process multiple items potentially, and the items are going to be stride apart from each other. And then next, we're going to go through basically the same while loop as before, except for now, instead of doing the modification, instead of updating the global histogram, we're going to be updating these local histograms. Okay, so again, we read a value from the array, and then we just update our local histogram we increase it by 1. Okay, and we keep going until we process all the elements. Okay, and then we do a sync threads here to make sure that all the threads in the thread block have processed all their elements. Okay, and then the final step over here is to take all of these local histograms and then add them and then combine them together into a global histogram. And the way we do that is, well, since these local histograms only have 256 values in them, right? So we only need 256 threads to do this. So so we're going to take the first 256 threads, and then each thread takes one index in the local histogram, and it just takes the value in the local histogram, at that index, and then adds it into the global histogram at that index. Okay, so that way, all of the different thread blocks are going to do this, right? And in the end, the global histogram is going to have the sum from all of the different thread blocks. So this is going to perform better than the previous algorithm. So one reason is that most of our atomic adds, right? So most of the time we spent, right? So this while loop is where we spent the bulk of our time. So most of this is happening on the shared memory histograms. And then there's also less contention because the only contention on the shared memory histogram is within a thread block, right? For the previous algorithm, we had contention between all of the threads on the same histogram, but now it's just within a thread block. And then in the end, we do have some global contention, but this is only, we only do this for one step, right? Because you just take the single value from the local histogram and add it into the global one. Okay, so next, we're going to look at a problem called aggregation. And then, okay, so one example of this, so aggregation is basically you take like a big piece of input data, and then you want to somehow, like find some statistics on it or something, and then you want to sort of shrink that piece of data. Okay, so an example of this would be filtering. So here we're going to be given an array, input array source it's going to have n elements, and we're also given like a predicate, which is like a condition. Okay, and then we're going to copy all of the elements from source that satisfy this condition into a destination array. So as an example, suppose we want to take the input array source and we just want to pick out all of the positive elements and then copy them into destination. Okay, so like a sequential program for doing this would be that we just go through all of the array elements, right? If it's positive, then we're going to copy it into the destination array. Okay. Sorry. And we have this pointer here indicating where we're going to copy the next value to. Okay, so each time we copy a new value from source into destination, we're going to increment this pointer. And at the end of this, the pointer tells us how many positive elements we actually copied. Right? So now we're going to look at several different methods for implementing this aggregation or this filtering operation. Okay, so the first one is going to be just the basic algorithm that's going to be done in global memory. And then we're going to move this to shared memory. Right? And then it turns out that there's actually a CUDA library called thrust, which has many useful functions built into it. And one of those functions is this thing called copyIf, which does exactly this filtering operation. So it copies a value if it satisfies a predicate. So we're going to compare the performance of these three methods. And then lastly, we'll look at something called warp aggregated filtering. Okay, so that's going to introduce some new atomic operations which work at the warp level. Okay, so the first version of this is going to be the global memory version. So here we're just going to take so we have a bunch of threads. They each compute an index. All right, now for this example, we're going to again assume you have the same number of threads as array elements. Okay, so then each thread just processes one element. So then each thread gets an index, and then it checks whether its index, the value from source at that index is larger than 0. And if it is, right, then it's going to copy that source value into the destination at this location nres, right? So nres is basically the current number of positive elements that the threads have found, right? So it's going to copy it into this nres location, and then after that, we need to increment nres, right? Because we found another positive element, so we increment nres, and we use atomic add to do that. Okay, so now you can probably guess that this is not going to work very well because all of the threads are going to be contending at the single variable nres when they do the atomic add operation. Okay, so now let's try to improve this. So now let's try to split this so that we can do this in shared memory. Okay, so what we're going to do is now let's see. Okay, so now each thread is going to process. Yeah, so each thread is going to process not just one element anymore. It's going to process this number of elements, this m per thread. Okay, and what it's going to do is each thread is going to iterate in this loop over here. So this is a for loop over here, and the first thing it's going to do is so this ln is being shared between all the threads in the thread block. Okay, so let's see. So the first thing we're going to do, so this ln is basically playing the role of nres previously. So the ln is counting how many positive elements the threads in this thread block have discovered. Okay, nres counts the total number of positive elements, but ln only counts the number of elements for this local thread block. Okay, so first of all, we want to set ln to be 0. And we just need one thread to do this, so therefore we're just going to have the thread 0 do this. Okay, and then after thread 0 does this, then we can go on. So therefore we need to sync threads over here to make sure that thread 0 has done this operation. Okay, so then next, we're gonna read a value from source, right? We're gonna read the ith value from source, and if it's a positive value, then we're gonna increment this ln here, right? Because ln counts the number of positive values. Okay. And then we're gonna make sure that all of the threads in the thread block have read their value and then incremented ln if necessary. Okay, so then we do async threads over here. Okay, and then now we basically so at this point, ln is equal to the number of positive values that this entire thread block has discovered. Okay, and we want to add this number into the global number of positive values. So therefore, we want to add ln into nres. Okay, but we only need one thread to do this. And so again, we're going to just have the first thread do this. Okay, so we're going to call him the leader. So if the thread with ID 0, he's going to do the atomic add of ln into nres. And then he's also going to get back the current value of nres. Okay, or sorry, the previous value of nres. So for example, if nres currently is equal to, let's say, 10, right? And if ln here is 5, because we found a total of 5 positive elements, right? Then here we're going to have ln be equal to 10 after this atomic add. Okay, but then nres becomes equal to 15. Okay, so then we do a sync thread to make sure that the leader thread has finished. Okay, and then next, now here we've just counted and updated nres, right? We've counted how many positive elements we found and then updated nres. However, we also want to store these positive elements into this destination array. Okay, so the next part is going to store these positive elements. Okay, and what it does is that we're going to use these variables position here. Okay, so position is basically so we have a bunch of threads that in the thread block that we're counting positive elements, and position indicates for each thread its position among all the threads in this thread block that found positive elements. Okay, so as an example of this, suppose you have 4 threads, okay, in the thread block. Okay, so 1, 2, 3, 4. Okay, and suppose the values that they have are let's say so this is the source array, right? So suppose the values are something like 0, 2, 3, and then like -1. Okay. So then what we want is we just want the second and third thread to, sorry, let me change this a little bit. Okay, so this is like, let's make this a 3 here, and let's make this a 1, okay? And this is the thread ID. Okay, so then we want the second and third thread to copy their values into the destination array, okay? So so the position here, right? What's going to happen is, so the first thread is going to have a he doesn't have a positive value, so therefore he doesn't do the atomic add. Okay, so at this point, so initially ln is equal to 0, right? So after so the first thread, he doesn't increment ln. Okay, the second thread does increment ln. Or sorry, let's do it this way. Okay, so we don't really know the order that the threads are going to execute in. Okay, so potentially we could actually have thread 3 execute first before thread 2. Okay, so thread 3, since he's got a value of 1, which is positive, he's going to do the atomic add, and he's going to get an ln value, or sorry, a position value rather. Okay, of 1. Okay, so ln is going to go from 0 to 1. Right? And then let's say that thread 4 executes. Okay, so thread 4 has a negative value, so he doesn't do the atomic add. Okay, so for him, the value of position is still going to be 1. Okay, and then let's say that so the order of execution. Okay, so we first have thread 3, right? So first it's going to be thread 1. Right. And then thread 3, and then thread 4, and then finally thread 2. Okay, so then thread 1, its position is going to be well, it doesn't actually do this operation, so it doesn't even get a position. Okay, so maybe I should write it this way. So it doesn't have anything here. Okay, so I'll just write an X over here. And then thread 2 runs last, And then when he does, so he's got a positive value, so he's going to run this atomic add over here, and he's going to add 1 to ln, and he's going to get a value of 2. Okay. So the point is that all of the threads with positive source values, right? They actually they do this atomic add, so they get a position value, and these positions are all going to be different from each other, right? Because each time you do, you increment ln by 1. Okay, so all the positions are different, and these positions are going to tell these threads where they're going to write into the destination array. Okay, so the way that this works is, oh, okay, I'm sorry. So I need to, so these values are incorrect. Okay, so thread 1, right, let me go through this again. Okay, I'm sorry about this. So thread 1, when he does this, he's got a negative value. He doesn't do the atomic add. Okay, so therefore he doesn't have a position. Okay, thread 3, when he executes, he does the atomic add, but he's going to get the old value. Okay, so he's going to get an old value of 0, and then ln is going to become 1. Okay, it got incremented. Okay, thread 4, he doesn't do the atomic add. And then thread 2, when he does the atomic add, he's actually going to get a value of 1, okay, for position, right? Because he gets back the old value, which is 1, and then ln becomes 2. Okay, so now, so finally, let's return over here, okay? So over here is where we actually write these source values into the destination. So, yeah, so imagine that, when we did the atomic add onto nres, right, suppose we got back the value 10. Okay, so that would mean that all of the other threads have discovered 10 positive values already. Okay, then what's going to happen over here is that each of the threads, right, if it had a positive value, okay, so D is the value that it read from source. And if this is positive, right, then that thread would have gotten a position value also, right? So just like, threads like 2 and 3 here, right, they got a position value, okay? And all of those position values are different, as we said, okay? So then, the actual position that each thread should write into is equal to the number of positive values that have been discovered up to now globally, which is 10, right? Plus the number of positive values discovered in this thread block, okay, which are these position values. Okay, so it's so the threads are going to take this value 10 over here, and thread 2 is going to add 1 to it, right? And then thread 3 is going to add 0 to this. Okay, so therefore thread 2 is going to write into position. So let me write this down here, right? So thread 2 is going to write into position destination 11, okay, 10 plus 1. Okay, and then thread 3 is going to write into position 10. Okay, and the value that they write is just the value that they read from source. Okay, so yeah, so after doing this, all the threads in the thread block have written their positive values, right? And then since we're going to have each thread process multiple values, then they're going to continue with this for loop until they've processed all their values. Okay, so that is the shared memory version of this. And yeah, and if you run this in practice, right, so so this example comes from, oh, I'm sorry, I forgot to say this. So the example comes from this website called DevBlogs. Okay, this is an NVIDIA website where many of their employees write articles about how to use CUDA and GPUs to solve various problems in very efficient ways. Okay, so this comes from this nice example that was given in the NVIDIA blog. And then so this article also did some benchmarks, and what we see is, so the benchmark is going to compare the global memory version of the aggregation of the filtering, right, with the shared memory version of the filtering. Okay, so the green one is the shared memory version, and you can see that the shared memory version is going to be quite a bit faster, and the x-axis here is the percentage of filtered items. Okay, meaning so it's like the percentage of positive items. Okay, now the more positive items there are, right, then the more contention there's going to be on these synchronization operations, on the atomic operations. Okay, so for example, if all of the items are positive, right, then there's going to be a lot of contention on this atomic add over here. Okay, yeah, so you can see that the performance actually decreases as the number of positive item increases. Okay, but for all of these different percentages, you have that the shared memory algorithm is a lot better than the global memory one. And then they also compared this to, let's see. So they also compared this to the thrust library. Okay, so remember that thrust has this function called copy if, which here you would say copy if the value is positive. Okay, so it does exactly what this filtering operation does. And so the copy if actually works in a different way. It uses something called a prefix sum. So it's working in a different way than this atomic implementation that we gave. Okay, and because it works differently, it actually has this property that the more filtered items you have, the better the performance. Okay, the basic reason is that if you have very few filtered items, right, very few positive items, then because the copy if is doing a prefix sum, there's actually not enough work for this prefix sum to do, okay, because there's very few positive elements. And so therefore you get sort of poor overall performance because there's not enough work for all of these different GPU threads to do. But as you increase the number of positive elements, then there's more and more work to do. So then you can begin to saturate the GPU. Okay, you can use up all of its resources. And so you actually see that the performance can increase a little bit. Okay, so now we're going to look at one last version of this. And so this is going to be warp aggregated atomics. And this is going to use new operations, which are these sort of warp-based intrinsic operations. Okay, so it'll introduce some new tools for us. Okay, so yeah, so the warp-based atomics, the way this works is, so up to now we've seen operations where all the threads in a thread block can see, for example, shared memory locations, and they can do atomic operations, atomic intrinsic operations on these shared memory locations. Now these warp-based atomics, right? This is an operation that is shared between the threads in a warp. Okay, so different warps cannot interact with each other using these warp-based atomics. However, threads within a warp can interact and synchronize with each other. Okay? And the synchronization and interaction within a warp is actually much faster than between the threads within a thread block. Okay, so these warp-based atomics are really fast compared to the sort of thread block-based atomics. And so you can get much better performance if you can somehow make use of these warp-based atomics. Okay, so so the way this is going to work is, let's just go through an example of this. So what we're going to have is, suppose you have a suppose you have a warp of threads, and so these x's indicate that other threads have already counted some number of positive elements. Okay, so we're again going to be just trying to filter out the positive elements, and other threads outside of the warp have already found some number of positive elements. Okay, and now this warp of threads is going to be processing these elements, right? And some of them are not positive, and some of them are positive. Okay, and what we want is so each thread is going to process one of these elements. So we have 8 threads over here, and so the threads with 0 values, they're not going to modify. They're not going to change anything because they won't be copying into the destination array, and only the ones with the positive values want to copy into the destination array. So each thread with a positive value needs to know where it copies its value into the destination array, right? Because all these threads need to copy into different locations in the destination, right? Okay, so what we should have happen is, for example, we can have this thread copy into the first location. So here the local offsets is basically saying for each thread, right, if you're going to copy into the destination array, where should you copy to? Okay, so for example, the first thread, right, it should copy to one larger than the previous number of positive values. Okay, so previously we found 4 values, and so this thread number 2 over here should be copying into location 5. Okay, thread 6 right, it's also got a positive value, so it should copy that into location 6. Okay, threads, so let's just label these. So this is threads 1, 2, 3, 4, 5, 6, 7, 8. Okay, so threads 4 and 5, they don't copy anything because they don't have positive values, right? And then threads 6, 7, 8, they do copy into the destination array, and they should place their items at locations 3, 4, and 5. Okay, so this is what we want to achieve. And the way we're going to do this is that now all of these threads over here, 1 through 8, they're in a warp, right? So what we're going to do is we are, let's see. So the first thing we need to do is figure out how many old values, how many old positive values have been found. Okay, so here there are 4 old positive values. Okay, so we only need 1 thread to do this. Okay, so therefore the warp is going to elect like a leader thread, and the leader thread is going to go find out how many old positive values there are. Okay, next, each thread is going to individually compute its own offset. Okay, so these different values here, right? They're being computed in parallel by all the threads within the warp. Okay, and then the leader, right? After discovering that there were 4 old positive values, he's going to broadcast this value, this 4 value, to all of the threads. Okay, all the threads in the warp. And then all these threads are going to take the old offset and then add their new offset to it. Okay, so the old offset is 4. So this thread, for example, is going to go to offset 5. Okay, and this guy is going to go to offset 6, and so on. And once they find the right offset, then they can go ahead and write their value into this offset location. And when you do this, this guarantees that all of the threads will write to different locations. Right? That's the main thing we want to achieve, is for all the threads to write their values into different locations, and also for there to be no holes in these locations. Right? Okay, so this is the code for doing this. So this introduces a bunch of these new atomic operations, which are all these operations with the double underscores. Okay, so let's look at what these operations do. Okay, so the first operation is this ballot operation. Okay, so you're going to call this ballot operation with a value, and remember that this ballot operation only applies to a single warp. Okay, and there are 32 threads within a warp. So the ballot is basically trying to find out which of these 32 threads is actually active. Okay, because sometimes you could have some threads want to do something and some threads don't want to do that thing. Okay, so we just want to count how many threads actually want to do this thing. Okay, so here when you run this ballot operation with 1, right, this is going to end up returning a 32-bit mask. Okay, and each digit in the mask corresponds to one of your 32 threads. And the digit says whether that thread is active or not. Okay. Yeah. So if you get something like all right. Yeah. So okay. So then we compute this mask, and now we can figure out which active threads there are. Okay. So basically, for our example, the active threads are going to be the ones with positive values. Okay. The inactive threads are not even going to call this function over here. Okay, the only threads which call this function are the ones with positive values, and so they would show up in this mask. Okay, now we want to take one of these active threads, right, and we want to make him the leader. So the leader is going to be the one that finds the old offset. Okay, so we want to have one of these active threads go find the offset, and let's see. And the way we do that is we're going to take this mask and we're going to use this operation here, find first set. Okay. So what that does is, if you have a binary number, let's say like 10110, okay. Oops. All right. So it's going to find the first set bit in this number. Okay. In this case, it's going to be this bit over here. Okay. Yeah, and you need to subtract 1 from this because of this off by 1 thing. Okay, and then this is going to be our leader. Okay, so basically all of so this is our mask over here. Okay, so this is which threads are active in the warp, and suppose there are only 5 threads in the warp. Okay, so we have so now we're going to take this thread, the second thread, to be the active, to be the leader. Okay, and now the leader is going to find how many old positive values there are. Okay, so this counter here is going to be the number of old positive values, right? So that was the 4. The 4 in this example. Okay, and then also he needs to, so the leader also wants to allocate space for all of the threads in this warp that have found positive values. So here we have 5 threads that found positive values. Okay, so the leader actually wants to set the offset to, right. So the leader actually wants to change the offset to 9. The leader wants to make the new offset be at this position. Okay, so the way he does that is, well, he needs to count how many threads from this warp have positive values. Okay, now remember the mask is indicating which threads in this warp have positive values. So in this case, it's going to be 3 warps. 3 threads have positive value. And so the way the way to know how many positive values there are is just to count how many 1s there are in this mask. And that's what this operation does. So this is called population count. Okay, so here, if you give population count a 32-bit value, it's just going to count how many how many 1s there are in that 32-bit value. Okay, so in this example, it would produce 3. And so therefore, when you do the atomic add, right, you're going to increase the counter by 3. Okay, and the rest here, this is going to be the old value of counter. Okay, so counter, the old value here is going to be 4. And the new value would be, well, here it would become 9. Okay, now next, we said that the leader actually wants to tell all of the active threads about the old offset. Okay, so this shuffle operation, this is actually kind of like a broadcast operation. Okay, so the shuffle is going to say, I want to broadcast this value. So this value is the old counter value, right? And who is going to do the broadcast? It's going to be the leader. Okay, so the second argument is who does the broadcast. And the broadcast is only to the threads within this warp. Okay, so all of these operations are with respect to only the threads in this warp. So only these 32 threads. Okay, and the final thing that we need to do is after all of the threads in the warp know the old counter, the old offset, right? Then they need to add their value into the offset. And so in order to do that, let's see. Okay, so now we're up to this point. Okay, so yeah, so what we want to do is, so every thread in the warp wants to find a position to write to. Okay, and the position of the thread is basically, now in this example, we're going to have threads, so let's say we're going to work in this direction over here. Okay, so now we want to find a position for these threads. So the first thread is going to find position, let's say position 1, right? This is going to find position 2. Right, the guys which are not active, the guys who are 0 in the mask, right? They don't even need a position, so we're going to ignore them. Okay, and then this final thread over here, he's going to find position 3. Okay, so we want somehow for these threads to produce these numbers 1, 2, and 3 down here. Okay, so how do we do that? What we're going to do is each thread is going to count how it's going to go now look in the opposite direction towards the right, and he's going to count how many threads before it actually have 1s. Okay, how many 1 threads are there before it? Okay, so for example, the first thread over here, right? He sees that nobody before him has a 1. Okay, so let's see. Maybe I want these values to be off by 1 here. Let's see. So the population count, Right, so I want these to be off by 1. So sorry, I'm going to change these 3 2 1s to 2 1 0. Okay, so this is what I want to have happen. Okay, so so the first thread over here, right, he should actually produce a value of 0. So how does he do that? Well, what he's going to do is he's going to take the mask, okay, this 1 0 1 1 0, right, and he wants to just keep the last 2 digits, or sorry, the last digit, okay, the digits before him. Okay, so how does he do that? Well, what he does is he's gonna take he's gonna do a bitwise AND of this mask with this number over here, which is 1 only in the final digit. Okay, so he's gonna do an AND over here, and what is this gonna do? Well, this is only gonna leave the final digit. Okay, because all of these preceding digits are gonna become zeros. Right? And it's just going to copy over whatever's in the final digit, which also here happens to be a 0. Okay, so that's what's being done over here, right? So the 1 shifted by lane ID. So lane ID, oh, I forgot to say this. So the lane ID, right? So each thread has an ID within the warp. Okay, so for example, this is the first thread within the warp. So he's got a lane ID of, so the lane, okay. So he's got a lane ID of 0. This guy's got a lane ID of 1, 2, 3, and 4. Okay? So the lane ID is just basically which thread are you within the warp. All right, so then if you take a 1 shifted by the lane ID, okay? So for example, this thread, right, he's got a lane ID of 1. So then if he takes 1 shifted by lane ID, right, so that's basically going to produce this number 1, 0 here. And then if you subtract 1 from that, right, then that's going to produce the number, that's going to produce this number over here in binary. Okay, because this number here is 2, right? 2 minus 1 is going to be just 1 in binary. Okay. Right, and then so he's so the first thread, he's going to produce this value all zeros, and then he's going to do a pop C on this. Okay, so he's going to count how many 1s there are in this value here. Okay, he's going to do this pop C over here. And he sees that, well, there are no 1s in this value. Okay, and that's how he computes his value of 0 over here. Okay, now let's do another example. Let's take, for example, this thread over here. Okay, so the fifth thread who has a lane ID of 4. Okay, so the fifth thread with the lane ID of 4, what he's going to do is he's going to do this part, right? So he basically wants to keep all of the preceding 4 digits. Okay, so he wants to take an AND of this mask, right? This is our mask over here. He wants to take an AND of this with 0, 1, 1, 1. Okay, so how do you get this value 0, 1, 1, 1, right? You do 1, you shift it by 4, right? And then you subtract 1. Okay. Yeah, and then when he does this, the output that he's going to get is, okay, so that's just going to keep the, so it's going to zero out the final bit over here, but it's going to keep all of the previous 4 bits. Okay, so we're going to copy the 0, 1, 1, 0. Okay, and when you do a population count on this, when you see how many 1s there are, well, there's exactly 2 1s. Okay, and so that's why this thread 4 over here, right, he can compute a position of 2. Okay, so that is basically what is being done by all of these threads, by this instruction over here. Okay, all the threads are just counting how many previous ones are there for lower lane threads. Okay, so that tells them, so that's basically the entire function that's being run by this warp. Okay, so after the warp runs this function, then every thread in the warp gets a position. Then the threads from the warp which have positive values, right? They're all going to get different positions, and then they can write their source value into the destination at that position. Okay, and the way we call this function is that we only want to call this for the threads with positive values, right? So we're gonna so now we have this function here. Each thread is gonna get an index, and then if it's got a positive value, right, it's gonna call this this aggregate, this warp-based aggregate function. Okay, and then it's gonna get a position back. So nres here is still gonna be the global number of positive values. Right. So initially, it's going to call this atomic aggregate increment with this nres value, right? And then it'll get back a position in the destination array, and then it'll write its value source into that position. Okay, so that's our first warp-based algorithm. And if you look at the performance of this, right? So here, the same article from the NVIDIA blog, right? It looked at the performance of this. So let's see. Okay, so it actually looked at two different architectures. So the first architecture was the Kepler. So that's kind of an older architecture. And what they achieved with these warp-based operations is up here, right? So they actually, so here they're getting about 100 gigabytes per second of bandwidth. Okay, so this is measured in terms of bandwidth because it's basically saying like how many values can you be filtering per second. Okay, so you can be filtering up to 100 gigabytes of values per second. Okay, so the higher this is, the faster your performance. And if you compare this, so they're getting about 100 gigabytes of performance. And even if you just do something like simply copying values over, okay? If you just look at the global memory bandwidth on this Kepler card, right, that is only about 180 gigabytes. So they basically, they got about half the maximum possible performance based on the, the memory bandwidth bound, okay, using these algorithms. Yeah, so the performance actually improves with the filter ratio. So right, so the more positive elements there are, the better their performance. And so this is because they write more values as you have more positive values. And the global memory aggregation worked faster than the shared memory one. So I'm not sure why this is, but that's what they observed. Okay, so then they also tried this on a different architecture, the Maxwell architecture. And here, the Maxwell actually has pretty efficient shared memory atomic operations. Okay, so even if you just go back to the method based on atomic add, but doing that in the shared memory, that is this green line over here. Okay, so even that gets pretty good performance. Okay, at least for low percentages of positive elements. Okay, so if you have a high percentage of these filtered elements, then again you have a lot of contention, and that's going to drive down the performance a little bit. Whereas for the warp-based algorithms, they actually get better performance as you have more positive elements. Okay, and overall the performance is lower over here because it's just it's a weaker card overall. Okay, this card only has like 5 SMs as opposed to the K40. Okay, so the final so now we're going to introduce a final set of atomic intrinsics, and these are called the shuffle operations. Okay, so the shuffle operation is also a warp-based operation, and it basically lets different threads within a warp share values. Okay, so it's like communication between the threads in a warp. Okay, so again, let's let lane here be the ID of the thread within a warp. Okay, and that's simply equal to the thread ID modulo 32. Okay, so it's always going to be a number between 0 to 31 because we have 32 threads in the warp. Okay, so we're going to look at 4 different shuffle operations. So the first one is called shuffle up. Okay, so here this is going to take a value var and then an integer delta. And the var needs to be a register value for the thread. Okay, so the thread is going to declare a bunch of variables, and some of them are going to be stored in registers. And you can and these shuffle operations allow you to exchange these register values between the threads in the warp. Okay, so the var is going to be a local register value, and then what this shuffle up does is that it's going to take so all the threads in the warp are going to have a copy of var, right? Sorry, each thread in the warp has its own copy of var, right? And they can all be different. And what the shuffle up does is that it allows it copies the value of var from one thread in the warp to a different thread, and it's going to copy from a thread that's delta lanes lower. So if you're a thread, then this shuffle up is going to copy the value of var from a thread that's delta lanes lower. Okay, so for example, let's say we have 4 threads, right? And then if delta here is equal to 2, right, then it's gonna copy. So we have 1, 2, 3, 4, right? So it's gonna copy from lane 1 into lane 3, right? And it's gonna copy from lane 2 into lane 4, right? And then these two threads, right? When they try to do the copy, they're actually gonna exceed the number of threads in the warp. Okay, so they actually are not gonna do anything. Okay, so the threads above lane 31 minus delta don't do anything, but all of the other threads are going to basically shift their value of var up by delta lanes. Okay, so shuffle down is just like shuffle up, except for you're going to copy your var to somebody who is delta lanes lower than you are. And then the shuffle XOR, so this is going to take a value over here, this lane mask, right? And what you're going to do is take your own lane and then XOR it with this lane mask. Okay, so that's going to produce a different lane. It's going to produce a number between 0 to 31, right? And then you're going to copy this value of var into that new lane, into this XORed lane. And then lastly, the shuffle operation. So we actually saw this for the filtering function, right? So the shuffle operation is going to take this this register var, and it's going to copy it over from whatever the source lane is. Okay, so if all the threads have the same source lane, then this is equivalent to a broadcast of this value var from the source lane to all the threads within the warp. Okay, let's see. Okay, right, so here we have to be slightly careful. So if you have a warp of threads, then they don't all have to do the shuffle operation, right? Because you could have, for example, a branch, and then some of the threads do go to one branch, which has a shuffle operation, and some go to a different branch, which doesn't have a shuffle. Okay, so the threads which actually do that shuffle operation, we're going to say those are the active threads. Okay. And the restriction is that you can only read values. So these shuffle operations are going to let threads read values. And you can only read values from an active thread, which is doing the shuffle operation. If you try to read values from a thread that doesn't even do the shuffle, then you can get undefined behavior. Okay, so let's use these shuffle operations to do something. So the first thing is let's just try to do a simple reduce operation, right? So reduce, we're going to do a simple sum reduce. So in this example, we're just trying to add up all of the values in this array here. Okay, so there are 8 threads, and then so the sum should be 8. So the way you do that is we're just going to call shuffle down a few times. Okay, so suppose in this example your warp only has 8 threads. So the first thing you're going to do is you're going to shuffle down by the size of your warp divided by 2. Okay, so shuffle down by 4. And you're also going to, so after you do the shuffle down, you're going to take your current value and then add it to the shuffled value. So what that does is, so the shuffle down is going to have these threads 4, 5, 6, 7, right? They're going to move their, so they have this value var over here, or sorry, not var, but v, okay? So they have this value v here. And the threads 4, 5, 6, 7 are going to move their value of v down by 4 lanes. Okay, and then the threads 0, 1, 2, 3, they're going to take their current value of v and then add it to this new value that they receive. Okay, so the first 4 threads are going to end up with values 2. So next, we're going to again do a shuffle, but this time we're only going to shuffle down by 2, right? So these are the v values, and if you shuffle down by 2, and if you add it to your current value, right, then these then now you get 2 4s, right? And then you're going to shuffle down by 1, right? And then you add these 2 4s together, and you get the 8. Okay, so if you have 32 threads, then you need to so in practice, your warp has 32 threads, so then you need to do this shuffle by 5 times. And if you compare the performance of this shuffle-based reduce versus something that, let's say, uses shared memory, it can actually be a lot faster. It's like 2 to 3 times faster based on their measurements. And then also, this will free up your shared memory, and you can use it for other things, because as we know, the shared memory is really small. Okay, now you might wonder whether you need to do any synchronization on this. So here, the nice thing about the shuffle operation is that because it's happening in a warp, and it's happening only among the active threads within the warp, right? Then remember, then all these active threads are actually SIMD, right? All these active threads are doing exactly the same instruction at each time point. Okay. If you have a warp where the threads are doing different instructions, then they would not do those at the same time point. You would actually break those different instructions into multiple time points, and at each time point, all the threads which are operating only do the same instruction. Okay, so therefore all of the active threads are doing the shuffle down and the plus. Okay, the plus equals, and so therefore you don't need any synchronization because everything is automatically synchronized due to the SIMD. Okay, so right, so we can also use this to do something an all reduce. So all reduce is, so the previous example reduced the values down to one thread, right? So of course you could have that thread just broadcast the value to all the other threads, and then you get an all reduce. But there's another way to do this, and it shows an example of using the shuffle XOR. Okay, so what we're going to do is we're going to shuffle XOR, and then the XOR requires a value that we're going to XOR with. Okay, so so each thread is going to take its own lane ID and then XOR it with this I over here. Okay, so the I is going to be just the powers of 2, so it's going to be 1, 2, 4, 8, and so on. Right? And so the way this works is that so it's useful to look at the IDs of the threads in binary. Okay, so here we have 16 threads. Okay, so we can write the IDs using 4 bits, right? So this guy is in lane 0. This guy is in lane 1, right? I'll do a few more of these. Oops, 1, 0. Okay, this is 1, 1, right? This is 1, 0, 0. Okay, let me do 2 more. Okay, so this is going to be 0, 1, 1, 0, and then this is 0, 1, 1, 1. Okay, and then so on. And so the way that this shuffle-based all reduce works is that whenever you do the shuffle XOR, right? So initially, the value of I is going to be 1. So therefore, for example, if you take node 0 over here, right? When he XORs with 1, he's going to get 1, right? So therefore, he's going to say that his value, right? Node 0 is going to say that he's going to take his current value of value, right? He's going to take his current value, and then also take the value from his ID XOR 1, right? And he's going to add them. Okay. Now, if you look at thread 1, right? He's going to take 1 XOR 1, and that's going to be 0. And so he's going to take these 2 copies of value and add them. Okay. Now this thread over here, the 0010, if you shuffle with, if you XOR with 1, you're going to get 0011, right? So he's going to do these 2 additions, and the 0011 is going to do these 2 additions. Okay, and so on. So in the so the first time that you do this, right, you're going to see that you get these butterfly operations over here. Okay, so each thread is just going to take the next thread and then add that value to itself. Okay, so so we have a for loop here. So the first iteration is you just take the next thread and you add the value. Okay. The next iteration of the for loop is that you're going to take nodes which are distance 2 away and you're going to add their values. Okay, because now in the second iteration, the value of I is 2. And so, for example, if you take 0000, right, and then you XOR with 2, right, you're going to get exactly 0010. Okay, likewise, 0001, XOR 2, you get that. Okay, right, so you get, so you get all of these patterns. Okay, so on the second layer, you XOR with, you add with all the guys which are distance 2 away. Right? In the third layer, you're gonna, so I here is gonna become 4, right? So you're going to end up adding with all the guys who are distance 4 away, and so on. Okay, so if you do this all the way up to 16, then at the end of this, you're going to have all the threads are going to end up with the sums of all the values. Okay, because here, right, after you do one step, you've added the sum with you combine these two values. Okay, and these guys have combined these two values. Okay, now when you do this, right, this ends up combining all 4 values. Okay, and then when you do this thing over here, right, well, let's see. So by this point, all of these threads have combined the values at all these threads is equal to the sum of all of them, of all 4 of them. Okay, and same thing over here. So when you do this operation over here, you end up combining all 8 of these values. Okay, so each time you do one of these layers, you double the number of values that you combine. Okay, so the final thing that we're going to do is we're going to look at we're going to use these. So previously we've used these operations just at a warp level, right? But of course you want to add up more than just 32 values. You want to add up many more values. So we're going to see how to combine these warp-based operations with global operations. So first, we're going to see how to do reduce on a block of values. Okay, and let's assume that the block has at most 1024 threads. Okay, so that's usually enough to get good performance. So that we'll make that assumption. So what we're going to do here is that each thread, first of all, it's going to compute its lane within its warp. Okay, so remember that's just going to be the thread ID modulo the warp size is always going to be 32 in our examples. Okay. Also, it's going to get its warp ID. So its warp ID is just basically, so each warp has size 32, right? And your thread block has some number of threads. So your warp ID is just going to be your thread ID divided by 32, right? That's which warp you're in. Okay, and then each warp of threads is going to call. So suppose we call the previous function, right? The function over here, right? Suppose we call this guy warp reduce sum. Okay, so this is going to take. This is going to allow a warp of threads to do a reduce. Okay, so we're going to call that, warp reduce sum, right? And then, so each warp of threads is going to call this warp reduce sum, right? So that's going to combine 32 values, okay, from the warp. And it's going to produce a single value, val. Okay, and now we're going to have the leader in each warp, which is like the first thread within the warp, right? He's going to take the sum of his entire warp, right, and then write it into this shared memory location, right? And the location is going to be based on which warp he's in. It's based on his warp ID. Okay. We make sure that all of the warps within the thread block have done this, right? So we use sync threads over here. And then finally, so since if you have at most 1024 threads in the block, right, and then each warp has 32 threads, then at most you have 32 warps. Okay, so this is why we made a shared memory array here of size 32, because at most the thread block produces 32 warp-based sums. Okay, and then so the final thing is that we want to add up all of the values in this shared array, and that will give us the sum of all the values in the thread block. Okay, and so to do that, we're first of all going to copy the. So we want to use the warp-based algorithm again. So then we're going to copy the values from the shared array into registers. Okay, because the warp-based so the shuffle operations only work on the registers, right? So we need to copy from the shared memory to the registers, and to do that, so each we only need the first. Let's see. Yeah, so we only need thread from the first warp to do this. Okay, so if your thread ID is less than dimension divided by the warp size, right, then you're going to copy from your lane of the shared memory into your register. Okay, and otherwise you don't copy. Okay, otherwise the value is going to be 0. And then finally, we're going to take the first warp of threads, right? Because we only have 32 values at most in the shared memory array, then we only need one warp of thread to add them up, right? So we're going to take the first warp of threads, and they're going to do the warp reduce sum to add up all of these values. Okay, and at the end of this, the val over here is going to be the sum of all the values in the array, and the array can have at most 1024 values. Okay, so then the final thing to do is, now what if we want bigger arrays, right? What if we have more than 1024 values? Okay, then of course we're going to need more than one thread block. Okay, so okay, so this example, they're gonna they want to limit the number of thread blocks in this example. Okay, so they're gonna say that at most you're gonna use 1024 thread blocks. You don't have to do this, but this is what they do in the example. Okay, so so therefore, if you have 1024, so they're gonna have at most 1024 thread blocks, and then each thread block is gonna have well, now they change it to 512 threads. Okay, so previously we could actually deal with 1024 threads, but here they only have 512. Okay, so that means that you can only deal with about 500,000 elements, right? Because if you assign only one thread per element, right? Because you have 500 threads per block, and you have 1,000 blocks. Okay, so now if you want to deal with more elements, more than 500,000 elements, then each thread will now need to process multiple elements. Okay, so therefore they're going to do this for loop here. Okay, so each thread is going to start at this index location, right? And then it's going to keep incrementing by this block dim times the grid dim. Okay, so this is what we've seen before. This is basically the total number of threads. Okay, so if you only have 500,000 threads, right? But let's say you have 5 million elements, then each thread needs to process 10 elements. Okay, so it's going to process the ith element, and then also process I plus the total number of threads, right? And then I plus 2 times the total number of threads, and so on. Okay, so first of all, each thread is going to go through all of these elements, right? Let's say 10 elements, and it's going to add that into this local sum thing over here. Okay, so right. And then after that, each thread in the block will now have a value sum, and then now we can call this block reduce sum. So the block reduce sum was this algorithm over here, right, which works for up to 1024 elements. Okay, and then right, okay, and then the so this is going to produce one sum value per thread block. Okay, and then we're going to write this sum value into this output array at this block ID over here. Okay, so at this point, each thread block has produced one sum. So we still don't have a global sum yet, because we need to add up these block-based sums. Okay, so what's going to happen in the overall kernel is that first of all, we're gonna call this this function over here, right? We're going to call it once using some number of blocks less than 1024, and then we're going to use 512 threads per block. Okay, so that's going to produce however many thread blocks you have. Let's say you have 100 thread blocks. Okay, so then that's going to produce. So then this output array here is going to have 100 values in it. Each value is going to be the sum from that thread block. And then the final thing you need to do is you need to do a reduced kernel on the output array. Okay, and that's going to add up all of the values in the output array. Oh, okay. So here's actually why they only use 1024 thread blocks. Okay, it's because each block-based reduced kernel can only work with 1024 elements, right? So here, when they call this reduced kernel, right, if they call it with only one block, right, then this can only deal with 1024 elements, and so therefore they need to make sure that this out over here only has at most 1024 elements. Okay, so out, there's one value of out for each thread block, so therefore you can have at most 1024 thread blocks. Okay, so I guess that's why they do it this way. All right, so then you call the device reduced kernel And then this is going to take all of the values from out and then combine them. Well, here they're going to write this back out to out, but this other out is only going to have one value in it, which is like the sum of all of the values that you have. Okay. So and this can work for any number of threads. Any size array, right? So if you have 1,000,000 elements, right, then each thread is initially going to have to process multiple ones of these elements, but then you call these reduced kernels twice, and then you get the sum of everything. Okay, so so that's all we're going to say about these intrinsic operations. So as I mentioned, there are other intrinsic operations, for example, for fast math calculations. So you can take a look at the NVIDIA documentation, and that's got more details about the other ones. Okay, but these are the ones that you would use for synchronization, and then the warp-based functions, they're not strictly necessary, right? Because you can do everything that you can do with the warp-based intrinsics using just like shared memory, but they work faster than shared memory, and so yeah. Okay, so so then I'll talk to you guys next time.